Should we begin? Hi, welcome everybody. Thank you for coming to this CaJAGWR seminar. Before I introduce our speaker, let me say that after the seminar we'll have snacks and drinks outside, right Max? So stick around for that. Okay, so our speaker today is Leo Stein, who is a senior postdoctoral researcher in Tapir, so third floor of Cahill. Leo's research interests include black holes, gravitational waves, general relativity, and beyond. So we'll hear a little bit about the beyond today. Leo received his Bachelor of Science in Physics with honor from Caltech in 2006. He then did his PhD at MIT with Scott Hughes, getting it in 2012. From 2012 to 2015, he was a NASA Einstein Fellow at Cornell, and he came to join us in Tapir in 2005. So without further ado, here's Leo, unless I missed something in the intro. Okay.
Thanks, Masha. Can everybody hear me? Yeah? Okay. Thanks to the organizers for inviting me to give the seminar. Thanks for everybody here in the audience for paying attention. I'm sure you'll remember everything that I have to say. So before I actually get started, I should say that this work is not done in a vacuum. I have a lot of great collaborators to thank. So I've worked a lot with Kent Yagi, who's now a professor at University of Virginia, Nico Yunus, who's faculty at Montana State University, Masha, who just introduced me, Baoyi Chen, who's another grad student up in Tapir. And all of the stuff that I'm going to be talking about today is done as part of the SXS, Simulating Extreme Spacetimes collaboration, where there are about, 8 or so SXS people here in the audience, including Mark and Larry and Saul. And all of this is taxpayer supported, so thank you for paying your taxes. So this is all your research too. Okay, so what I'm going to tell you about today is how to probe strong field gravity using black holes and gravitational waves, and how to learn something hopefully beyond general relativity. So before I get into that, I just want to give a little picture of the field as a whole. I'm sure that you all know this already because Jocelyn gave a good CaJAGWR seminar recently. We've heard a lot about all of the sources that LIGO has been detecting. So this is a picture of the stellar graveyard made by Frank Alevsky. Up in blue, we have all of the binary black hole mergers that LIGO has detected. All of the purple ones were the stellar mass black holes that were known from electromagnetic observations before, and now we have this big population up here that are known just from gravitational wave detections. Down here we have the graveyard of neutron stars that were known from electromagnetic signatures before, and now finally we have one binary neutron star merger that made something, we still don't know what it is, but in the future this is going to become a much richer picture. This is just from 01 and 02 of advanced LIGO. And the detector is currently being upgraded. We're going to have better sensitivity, and we're going to have lots and lots of detections. So instead of a cartoon picture, we're going to have a very detailed picture of the population statistics of black holes in the universe, binary neutron stars. There are a lot of things that we know that we are going to learn. We are going to learn things about the masses and spins of black holes, whether they're born in a cluster environment or field environment, what made them, what kind of stellar systems, how those things evolved. This is one of the known unknowns, and it's going to become a known known in just a few years. Then there are some of the things that we hope that we'll learn soon. So it would be really fantastic if we could learn something fundamental about neutron stars. So we'll learn we've already started to learn something about the relationship between neutron star mergers and gamma ray bursts, which was conjectured for a long time, and now there's real evidence that gamma ray bursts are actually mergers of neutron stars. So if we get more detailed observations, then maybe we'll learn something about the central engine of gamma ray bursts. What is it that actually makes these things? This is supposedly the origin of most of the R process elements in the universe. And with luck, if nature is really kind to us and the detectors work really well and people work hard at making them more sensitive, then we'll get access to the equation of state of dense nuclear matter. Right now, this is buried at high frequencies. But in the future, with better sensitivity and observations that are closer or just higher signal-to-noise ratio, we'll learn something fundamental about nuclear physics from gravitational waves. This is an unknown, a kind of known unknown that may become known in the next decade or next generation, hopefully. So these things don't really keep me up at night because I'm sure that we'll figure them out eventually. The thing that really keeps me up at night is whether or not general relativity is correct, which is what I'm going to tell you about today. So why should you care about this topic? Why should you care whether or not general relativity is complete? So we know that general relativity is a beautiful theory, and it describes all gravitational phenomena that we see in the universe today. But fundamentally, it has to be incorrect, just at the level of this left-hand side of Einstein's equations is a classical tensor field. These are just numbers. And the right-hand side is a quantum mechanical operator. So this is a type mismatch. So you can't set a scalar, or we can't set classical numbers equal to quantum operators. So this equation doesn't make any sense. So people have tried, of course, since as long as general relativity has been around, to come up with some quantum theory of gravity. So they've tried doing just the straightforward quantization around Minkowski space, and you soon learn that general relativity is non-renormalizable. So that's a hint that there has to be new physics, and we don't understand it yet. But even if you're not that worried about it, maybe you say, fine, there's something semi-classical. We don't really know how to treat it yet, but semi-classical relativity should probably work, right? Let's just treat this as being sourced by something like the expectation value of the right-hand side. But still, there's a hint that there has to be new physics in the gravity sector that we don't have control over yet. So the best hint of that is from the black hole information paradox. So let me jump ahead to that. So this is the conformal diagram that you usually see for a star collapsing into a black hole, and then that black hole eventually radiates away and shrinks to something that has zero mass. And back here at early times, curvatures outside of the horizon are fine, and the singularity is hidden behind the horizon. And if you're only interested in semi-classical gravity, then you don't care. But all you have to do is just get a rocket pack and fly next to the horizon and just wait long enough. And eventually the black hole evaporates, and outside of the horizon you get curvatures that are arbitrarily large. So semi-classical GR plus quantum field theory just doesn't work. All you have to do is wait. Outside the horizon it breaks down, and you get arbitrarily large curvatures. So we know that there's something new to learn about gravity, no matter how you look at it, whether it's from the fundamental point of view or just we don't really understand yet, so let's use semi-classical. No, there has to be new gravitational physics. Okay. So there are a number of different approaches for trying to learn something new about this theory that we still don't really fully understand. So you could go to our colleagues across the street, go to the high energy people, and look for UV completion. And this could be something like string theory, loop quantum gravity, causal dynamical triangulations. There's lots of different approaches that people take from the top down to try to build like full, exact quantum theories of gravity. So I'm not going to do that because I'm not clever enough. Instead, I think that we can still learn something just by looking at classical general relativity. There's still things to learn. And then I'll tell you about beyond GR. So this is just a teaser for things that you can do in classical general relativity. So I already told you why you should be interested in studying black holes. We know that something like quantum mechanics can be important at the horizons, even though if curvatures are weak. So studying black holes, studying non-rotating black holes is easy. People have been doing that since the 60s. You can do linear perturbation theory, and because spherically symmetric black holes have a lot of symmetry, they're easy to study. When you have rotating black holes, there's not enough symmetry to use the tools that you had when you were looking at spherically symmetric black holes. So you can't use this metric perturbation formalism. Instead, we rely on what Saul taught us, which is called the Tucholsky formalism. So instead, we use curvature perturbations. This is very difficult because if you want to go back and ask what was the metric doing from these curvature perturbations, you have to do this complicated procedure where you're not actually finding curvature perturbations, you're finding Hertz potentials, and then you use this metric reconstruction procedure. It's very complicated, and I don't recommend it. But But there's something special that happens if you take the spin of the black hole and you send it to 1. So if you send the spin to 1, this is also from one of Saul's papers back in 1972. This is a nice embedding diagram. If you go really close to the black hole, you find that there's a kind of emergent symmetry in the throat region of the black hole. So down here, you kind of won't be able to tell how far away from the event horizon you are, because you can just rescale this whole cylinder up and down, change your distance from the horizon, and also change how fast your clock is ticking, what redshift you experience. And that's an exact symmetry of this near horizon region. So when you zoom into this region, which is called near horizon extremal Kerr, you get an extra symmetry, and it turns out that you get yet another extra symmetry. And this means that you have enough tools to actually do metric perturbations again. So you don't need to go through the Tucholsky formalism. So in this recent paper with Baoyi Chen, we showed that you can do metric perturbations in near horizon extremal Kerr. You can separate them, and so you don't need to go through the Tucholsky formalism. This is an interesting arena to study because this is where there's this conjectured Kerr conformal field theory duality that suggests that maybe black holes are a kind of critical point. All right, this is just a teaser, and if you want, we can talk about it later. Whenever you see the symbol, that means ask me later. Okay, so there's still tough stuff to do just in classical general relativity. Okay, and then going away from like the fundamental theory side of things, there are things that you can learn just by asking nature. So hopefully, nature will give us some hints about what the real nature of gravity is, if it's not general relativity. So we want to go and test general relativity in all of the regimes where we haven't yet tested it. So far we have precision tests in the weak field regime, in the solar system, in pulsar binaries. But there are a lot of theories that give you the exact same phenomenology as general relativity in the weak field regime. So we need to go to places that we haven't explored yet, the strong field where curvatures are large, where time derivatives are just as important as spatial derivatives, and where nonlinearities are important. So here's a little picture of a cartoon of gravitational phenomena in the universe and different ways of saying where the strong field is. So on the horizontal axis, there's the Newtonian potential when that thing makes sense. So on the left, it kind of makes sense. So as you get close to 1, it doesn't really make sense. So all black holes lie here on this strip at order 1. And on the vertical axis, there's the curvature, or 1 over the curvature radius squared. It's a dimensionful quantity. And going up is getting to shorter curvature radii. So this is essentially all gravitational observations that we can make in the universe on one plot. This is from Tessa Baker's paper. So down here we have cosmological probes. Here we have stuff in the solar system, pulsar tests, satellite tests. These are the S stars that are going around CaJAGWR star in the center of the Milky Way. Here are supermassive black holes. And all the way at the top right, these are the events that LIGO is measuring up here. So this is the regime where we haven't yet done precision measurements. We have precision measurements down here. And we would like to have access to this new neighborhood up there. Okay, so here's the big picture view of testing GR, precision testing GR. In the past, we've had precision tests in the weak field. And weak field means distantly separated compact binaries. So now I'm going to have a digression on what it was that we were doing in the past. Okay, so with distant compact binaries, you can use something called the post-Newtonian formalism. So in this formalism, you kind of build a theory where you replace your binary, each of your compact objects, with a point particle with a bunch of properties that describe its structure. So these properties are the multipole moments of the body. This is what you learned in sophomore year or freshman year physics, depending. So I learned that in Phys 106. So the multipole moments of the body are all that you need to know far away. This is a picture of the Earth. This is the gravity field of the Earth. If you're a satellite going around the Earth, all you care about is the monopole and maybe the quadrupole and octopole, a few moments. So you don't care about the detailed structure of this. And the same thing is true when you have widely separated neutron stars and black holes. All you care about are just its first few non-vanishing metric multipole moments. Now what happens when you change the theory of gravity is that you can have different types of multipole moments arise besides just the metric ones. So people call these things hairs. So if you change the theory to something like Brans-Dicke theory, then you can have a new scalar field, and you can have a scalar monopole moment for certain types of bodies. So specifically in classical scalar tensor type theories, neutron stars do have scalar charges or monopole moments, and black holes do not. But if you change the theory in a different way called Einstein-Dilaton-Gauss-Bonnet, then you have the reverse situation, where neutron stars do not have scalar charge, but black holes do have scalar charge. And in dynamical Chern-Simons, which I'll talk about later, instead of charges, these things act like dipoles, which are like little bar magnets. So one of these proofs, there's a nice proof by Sotirio and Zhu about these properties. I'll mention this particular X here for neutron stars. This is a nice topological proof from me and Kent and Nico. So if you want to see how topology can make it into gravity theories, then go look at this paper. And it relies on the fact that this Einstein-Dilaton-Gauss-Bonnet theory has this thing called the Gauss-Bonnet density appearing in it. And if you integrate over it, you can learn that for neutron stars, their scalar charge has nothing to do with the structure of the body, and it's the same as if there was no body there. So ask me about that later if you care. So this makes it seem like your task in studying the motion of compact objects in different theories of gravity is kind of hopeless, because you have to go theory by theory. What are these moments, and then what does that mean about their motion around each other when they're in, say, a pulsar binary? So one thing that you can do is you can split up the work. So in this paper from me and Kent Yagi, you can do a kind of parametric approach where you say, let me throw away what the theory is and just say parameterize it at the level of somebody tells me that the theory generates, scalar charge or scalar dipole moment or scalar octopole moments as the leading correction. And that automatically tells you, with just a little bit of work, what kinds of things you might see in pulsar timing experiments and gravitational wave experiments. So you split this task up into what do you know about the orbital dynamics versus go get your theory and do some matching calculations and figure out what those moments are. And then you can plug it into this toolkit that we developed. So this is the same diagram as before from Tessa, except I made it in Mathematica, so it's not as pretty. So here again is the Newtonian potential and the curvature radius. And here are some pulsars. Here's J0737-3039, which is the double pulsar binary, except one of them turned off. And we were able to predict what kind of pulsar timing bounds you would be able to place on these two different theories. And then we checked with more detailed calculations, and they agree. So this parametric framework is one approach. Okay, this is all still in the weak field. So back to the big picture. That's what we had access to before for precision tests. Now we finally have access to the strong field regime. This is, of course, GW 150914. And this was able to get us tests at the, say, 5% level of general relativity. In the future, we would like to be able to test general relativity to more like 5 decimal places. So we want to do precision tests of general relativity in the strong field regime. And that means either black hole mergers or neutron star mergers. Unfortunately, for neutron stars, you would first have to convince everybody that if you saw something different from GR predictions, that what you were really seeing was something due to gravity and not something due to funny business with nuclear matter or other matter that's floating around. So from my point of view, the only option for doing precision tests of general relativity where there aren't any uncontrolled unknowns is with black hole mergers. Okay, so then how do you do precision tests with black hole mergers? All right, there are two general approaches to doing precision tests. You can either have a theory-specific approach or a theory-agnostic approach. I already touched on this with splitting up the work with just the orbital motion versus matching the multipole moments. So the nice thing about the theory-agnostic approach is that if you do a bunch of work, then you can reuse it for all theories. And there are a bunch of frameworks for this. In the weak field, we have parameterized post-Newtonian. at the level of waveforms, gravitational waveforms, we have something called parameterized post-Einstein, which I'll mention later. But the difficulty is understanding what those things actually mean at the level of the theory. Okay, so here's the thing called parameterized post-Einstein framework. This is something that Nico and Franz came up with in 2013, or I don't know, 2010? So the idea is just to take your predictions from general relativity. So this is the waveform, the gravitational waveform prediction, Fourier transform it, go into the frequency domain, and then just multiply by some correction factors. That's all you do. You just multiply by some correction factor, 1 plus some correction, and then a phase correction, which is and both of these are in the form of a power law in frequency. So U is a frequency parameter that has some sort of physical meaning. And then you try to figure out what these 4 different parameters, alpha A, beta B, are allowed to be from the data. So this is something that LIGO did in the testing GR paper with 150914. So each of these columns is for one particular value of B. And then if you turn your head sideways, what you get is a posterior distribution of the allowed values of beta. So this is a thing that you can do. But the question is, what does it really mean at the level of the theory? Where did this form even come from? So I'll tell you, this form came from doing post-Newtonian calculations in a bunch of different theories. And these are calculations that I've done, that Nico has done, a lot of other people have done. And in the weak field regime, when these bodies are widely separated, what you find is that whenever you deform general relativity, you almost always get these power law corrections in amplitude and phase. I don't think that there's an example yet where we haven't seen this. So that's good motivation for this parametric form when you're in the weak field regime. So the point is that when you're expanding in powers of frequency, what you're doing is really expanding in powers of velocity or separation of the binary. But the problem is that over here in GW 150914, the velocities are order, a tenth of the speed of light or half of the speed of light. So you don't really have a good expansion parameter that you can use to justify why you're using this parametric form. So it's something that you can do. You can throw it into Monte Carlos and get these posteriors, but you don't really know what it means at the level of a theory. So what should you do? Okay, so it would be nice if we had a better justified parameterization, if we had some guidance for what kinds of deformations away from general relativity you might see in different theories. But we don't really have any guidance from theories yet. And the reason is that we haven't had any simulations of binary black hole mergers in other theories with an asterisk. And that's what I'm going to tell you about for the rest of the talk. Okay, are there any questions so far? No? Everybody still awake? Yeah.
So you just told us that there's this really nice framework, and every theory you've looked at seems to fit in it. So tell me again what we're going to learn from these simulations. What is it that's motivating the simulations and what we're going to learn?
Good. Okay. So in fact, this form that you get an exponential with power laws and frequency is the exact same thing that you get in general relativity in post-Newtonian calculations. But we know that those calculations break down when you get to the merger regime. Yeah. Yeah. Good. Anything else? Zach?
So would you explain the quantum rank a little bit?
Yeah, so in every one of these columns, just take each column individually and turn your head sideways and just this is up, this is left-right symmetric, so just ignore half of it. Then what you see is a kind of a bell curve. That's just the posterior distribution of the parameter that's on the vertical axis, which is really the value of beta associated with that B. So each of these columns is a different B. Good? Okay. Okay, so the problem is we don't have binary black hole merger simulations in different theories. So the reason we don't have it was nicely summarized by this quote from Franz Pretorius and Luis Lehner in 2014. This is in a review article. So despite the large number of proposed modifications to general relativity, none have yet been presented that are consistent in the weak field or in the regime where it's well tested. predict observable deviations in the strong field, and possess a classically well-posed initial value problem in the strong field regime. So there's kind of a necessary condition to do these simulations. And it all comes down to this thing called the initial value problem. So now I have to tell you a little bit about numerical relativity, say what is this initial value problem thing. So numerical relativity is taking Einstein's equations and putting it on the computer to try to evolve spacetimes. So Einstein's equations are nonlinear, second-order hyperbolic partial differential equations, 10 functions, until you do the 3 + 1 splitting, and then you get 50 functions all over spacetime. People have actually been trying to do numerical relativity since the 60s, and finally in 2005, all of the ingredients came together that made it possible to actually evolve through merger. So what we get out of these simulations, now I get to show you a movie that I didn't make. All right, so, rendering artifact. All right, so what is it that you're seeing here? So this is from some spec simulations and then visualized. So you have the metric fields all over space-time. Then we take a slice through space-time, and on this slice, you see a bunch of different metric quantities. These are essentially the directions that the coordinates want to fall. The colors correspond to how quickly your clock is ticking at that point in space-time, and the depth of the surface has to do with how curved space-time is. And down here you see the waveform that comes out of the simulation. So to evolve these things, you have to be able to take data at some time, take metric data, and then uniquely solve for what the metric quantities are going to be at a later time step. So how do you know whether or not you can do that? That is the content of whether or not your theory has a good initial boundary value problem. So it's difficult in general relativity because this theory is both under and over constrained. It's under constrained in the sense that this theory has gauge freedom, so you don't have a unique solution unless you fix the gauge. And it's over constrained in the sense that when you split this up into space-like hypersurfaces, you're not allowed to just choose data freely on those hypersurfaces. The data that you choose has to satisfy certain constraints. It's further made more difficult because you have singularities. So in our code, we cut the middles of the black holes out so we don't have singularities inside the computational domain. These constraints are challenging because if you think of the constraints in the infinite dimensional field configuration space, then the surface, the real surface of geometries that are allowed is the surface where constraints are equal to 0, but this is an unstable surface. So if any numerical noise pushes you away from that surface, then you probably blow up away from it exponentially quickly. So you have to do this constraint damping stuff. The point of this is to tell you that it's not trivial. That's why it took from the 1960s until 2005 to do this. And every other gravity theory that you can think of that we care about is going to be at least this difficult. So I'm saying this because the only gravity theories that I care about are the ones that are sufficiently close to general relativity that they are consistent with the black hole mergers that we've seen so far. So it has to be, in some sense, close to general relativity. So in GR, we know that we have a good initial boundary value problem. Here are some example theories where we also know that we have a good initial boundary value problem. This is scalar tensor theory, or a class of theories called scalar tensor. That's just the Einstein tensor, and the rest of this stuff looks like a source term. Here, there's box acting on a scalar field, and some stuff that has to do with matter and maybe a potential. So we know that this has a good initial boundary value problem. So people have simulated this theory on a computer. The problem is that this thing doesn't predict anything different for black holes smashing into each other. Because if you only have black holes, then you don't have any matter. So throw away that T, throw away that T. If you have a massless scalar field, which is the only type of scalar field that you would care about for long-ranged forces, then you throw away the potential. So this thing would pretty soon settle down to 0 because you have a kind of no-hair theorem. And then you'll just have Einstein's equations with 0 on the right-hand side. So that's identical to what you would get from Einstein's equations. So this theory, you can't distinguish it from GR using black hole mergers. There's exactly one other theory that I'm sure has a good initial boundary value problem. That's Einstein-Maxwell-Dilaton. And there's only been one simulation of that I'm aware of, and that's this paper. Okay. So there are about 1 million different ways that things can go wrong in your theory for spoiling a good initial value problem. Ask me about this later. The point is that there's a lot of potential pitfalls. You could have something called the Ostrogradski instability. You can try to cure that in certain ways. Even if you try to cure that, you might run into some other problems like ghost degrees of freedom. You might end up with a theory that's not quasi-linear, and then if you try to solve this, then your fields suddenly go from being real to being complex, and that's no good. And then there's this work on a specific class of theories. This is the most detailed work on whether or not this other class of theories has a good initial value problem, and it looked pretty bad for certain subclasses of this theory, but it's still an open question. So there's a lot of ways that things can go wrong. Okay, so let me tell you a way to make things right again. The idea is one that we now use in essentially the rest of physics and not testing GR. So why don't we use it in GR too? So in condensed matter physics, in particle physics, all of our modern formulations of theories is that we don't really think that they're fundamental theories. We just think that they're effective field theories. They only have to describe the physics that we have access to in a certain range of energy scales or length scales. So I don't care that, say, the standard model doesn't describe physics all the way up to the Planck scale, because I'm just doing experiments at, a few GeV or a TeV. It doesn't matter. So this was even kind of known way back in the day. So before we understood the weak force, there was just the 4 Fermi interaction to describe weak decay. And the 4 Fermi interaction is not renormalizable. You lose unitarity above the weak pole. And that unitarity is restored with electroweak symmetry breaking. But at low energies, if you take electroweak symmetry breaking, you just get an effective field theory with the 4 Fermi interaction. So that, low energies, you recover this non-renormalizable theory. So this works in condensed matter and particle physics. Let's use it in testing general relativity as well. The idea is that general relativity is an effective field theory if you look at it right. In fact, it has some smaller effective field theory sitting inside of it, like post-Newtonian theory. And there's probably a bigger effective field theory sitting outside of it. So we're going to go from the bottom up and say, let's add some higher order operators and see what that does to the predictions of the theory. And as long as we're sufficiently far below the energy scale where it stops being able to make predictions, then it's fine. Okay, so in quantum theories, losing predictivity was the same as losing unitarity. In this classical partial differential equation, losing predictivity is the same as not having a good initial value problem. Those are the same thing. So the idea is that as long as you're at energies below your cutoff scale or distance scales that are very long compared to your grid size on your computer, then your theory is going to be well posed in powers of the ratio of these length scales or energy scales. So the idea is that if we're adding something to the theory, we're going to have a new length scale, and we're going to assume that that length scale is so short that we can use perturbation theory to control the calculations. So I'm going to give you one example for the rest of the talk. So this example is called dynamical Chern-Simons gravity. So let me just give you the background on this theory. There are some fundamental theory reasons to care about this, but you can look these up later if you really care. For the purposes of this talk, all you should care about is that it's general relativity plus something kind of like the QCD axion, except instead of being coupled to QCD, it's coupled to R dual. So that kind of looks like the QCD axion interaction. So what you get from this theory are field equations where you have Einstein's equations plus some correction here. There's a little epsilon that's related to this new length scale that we're adding to the theory. And I've highlighted that the fact that there's third derivatives of the metric here, which I'll come back to later. And then you have a scalar field that's sourced by this R dual thing. Okay. So I should note that this RR dual thing is related to like local rotation in space. So what you get from non-rotating black holes is the exact same thing as you get in general relativity. If you have no rotation, then you don't source this, the axion thing. It's just a Schwarzschild black hole. But as soon as they start rotating, black holes start to generate this axion field. So here's a little movie. Every frame in this movie represents a different rotation of the black hole. Let me move this down. So what you see here are level sets of the axion fields. And as I play the movie, the rotation increases from the dimensionless 0 to dimensionless 1 angular momentum parameter. And you can see that these level sets are moving out, so this axion field is getting stronger and stronger. And for the most part, for all values of rotation, this axion field has kind of a dipole configuration until you get to very large values of spin, and then there's some funky stuff. So, pause. Hello? Okay, this thing doesn't want to scrub. Okay, anyway, there's some complicated multipolar structure when you get to very close to extremal, which is not that important for the rest of this talk. Okay, so black holes in this theory have this kind of dipole structure. And when you put them together, that means that they have a new interaction that's mediated by this axion field. It's like two bar magnets that are going around each other, and they kind of torque each other, and that changes how quickly they precess. And because you have this extra axion thing, the axion itself can radiate. So here are some references if you want to see some of the phenomenology of this stuff. Most of the post-Newtonian phenomenology was worked out by me and Kent and Nico and Takahiro Tanaka in this paper. So we already have analytical predictions for what binaries do in the weak field regime from this paper. Okay, so let's come back to the question of how you actually simulate this thing. So I highlighted that third derivative of the metric thing. And as I mentioned on an earlier slide, third derivatives usually mean that you have something called the Ostrogradsky instability. So you should expect that this theory, as an exact theory, does not have a good initial value problem. In fact, that was almost proven in this paper from Terence Delsat and Helvi Witek and David Hilditch. But they're very conservative people, so they said it's not a proof, but you should believe what they said. You shouldn't think that this theory, as an exact theory, has a well-posed initial value problem. But if you expand things order by order in that epsilon that I introduced, at every order in epsilon, all you have to invert is the same thing that you have to invert in general relativity to solve for the metric. So the statement is that the order by order in epsilon, the equations are well posed. So I'm not going to show you the derivation, but if you really want to see it, then ask me later. But the claim is that because this theory is close to general relativity, in the sense that if you send epsilon to 0, what you get is just Einstein gravity plus some scalar fields that's not coupled to anything, and then it just goes away. Because it's controlled, because it's close to general relativity, the structure of being able to solve for the metric is controlled by general relativity. Okay, so those are the words that I hope you believe, but we actually have pictures to back them up. Yeah?
I wanted to ask you, the idea that these theories don't have a, if I'm getting the language right, well-posed initial value problem, is that a fundamental problem for the theory?
So the theory could never be an exact, UV completion or fundamental theory, in the same sense that the four Fermi interaction is not the real description of weak decay. It's just some low energy description. But, it can give us insight into what's really going on if we, measure things and see which interactions are allowed. Yeah. The motivation is this stuff. So it comes from anomaly cancellation. If you have chiral theories in curved space-time, then you generate triangle anomalies that are sourced by RR dual. And if you want to cancel those anomalies, then you put in an anomaly cancellation term into the action. So this is kind of like a Peccei-Quinn type cancellation. Or you could just view it from the pedestrian point of view, which is what I like more, which is that it's a bottom-up EFT instead of a top-down EFT. So, look at all of the possible effective field theories at this operator order. And this is the one that has different phenomenology from the other ones. There are 3 other ones that you can build at the same order, and they all have the same phenomenology because they're all mediated by some parity-even interaction. This one is mediated by a parity-odd interaction, so it's unique. There are other reasons why this one has good properties, which you'll see in a later slide. Okay, this is the claim. The claim in words is that because the background dynamics, because general relativity is well posed, then the perturbations are well posed. But don't just take my word for it, because we made a movie. So what are you seeing in this movie? So this is from a bunch of simulations that Masha and I did. There are 2 black holes going around each other, and again, we're visualizing level sets of this axion field. So here's the location of one black hole. You have something like a dipole. Here's another black hole. There's another dipole. And these 2 dipole fields are kind of interacting with each other. You have some 3-to-1 mass ratio. The spins are both aligned, pointing in the z direction. You see them go around. And then let's look out at the far field regime. So there's radiation coming out in the axion. So now here's a pop quiz. What is the radiation pattern? I'll show you a few more cycles of it. If I already told you the answer before, then let somebody else answer. So what's the radiation field in terms of multipoles? Masha knows. Okay, well, I will tell you the answer because I'm running out of time. So there's a 0 crossing in the orbital plane. There's a 0 along the orbital axis. There's no radiation going up and down to the North Pole, so that's a quadrupole. And it's important that it's a quadrupole because that means that this theory isn't like automatically ruled out by binary pulsar tests. Okay, so the black holes just merged. Let's go back and look at the radiation zone again. So you see that out here we had that quadrupole radiation pattern. Now we have a dipole radiation pattern, positive in the northern hemisphere and negative in the southern hemisphere. Okay, so we've learned something new from this burst of dipole radiation at merger. All right, so let me make this more quantitative. We can decompose the radiation field into different multipole moments. Let me zoom in on this. Okay, so this top panel here is what's called psi4, curvature scalar. This is what we usually look at for gravitational waves in general relativity. This is just the result that you get from GR. And all of the 3 lower panels are the perturbative results for the axion radiation field. So here's the dipole component. You can see that at early times there's no radiative part to the dipole fields. And then at merger, there's a burst of radiation. So the solid curve is the numerical simulation, and the dashed curve is the prediction from me and Kent and Nico from 2011 or whenever that was. So you can see that there's good qualitative agreement. So the post-Newtonian calculations that we did in the weak field could never have predicted that we have a burst of dipole radiation at merger. This is something that you can only get by doing numerical simulations in the strong field regime and actually slamming the black holes into each other. So the dominant source of radiation for most of the lifetime of this thing in the axion is the quadrupole radiation field. And as I said, that's important for this theory not being already ruled out by binary pulsars. And again, there's qualitative agreement between the analytical results that we had from before and these numerical ones. And then we even have higher modes. So here's an octupole mode. I have to zoom out. Sorry. Not that far. All right. So let's talk about what you can actually extract from these types of simulations. So we can get the energy flux in gravitational waves out. That's the top solid, the dashed dotted line. And then you can also ask, what is the energy flux in the axion fields coming out? So these 3 curves are for 3 different runs that we did where both of the black holes had different spins, so 30%, 10%, or 0% of maximum spin. And again, there's kind of qualitative agreement between the numerics and the post-Newtonian calculations. And again, there's a burst of axion flux at the end, where there's a lot of radiation coming out. Okay, so this was all doing perturbation theory at order epsilon to the 1. And this got you the axion field, but it didn't get you the correction to the gravitational field. That's what happens at order epsilon squared. So the next step is to go to order epsilon squared, and Masha is already hard at work coding this up into spec. So there are going to be new difficulties that arise in the future. Instead of just one set of gauge and constraint that we have for the metric in the background, we have two sets of gauges and constraints. We have to worry about finding a stable gauge for the evolution scheme. There's some interesting questions about stability that we haven't run into them yet, but maybe we will in the future. And because this is a perturbation scheme, you have to ask whether or not the perturbation is internally self-consistent, whether or not you are within the radius of convergence of the calculation. And then there's some other questions which you can ask me about later. Okay, so this question about the regime of validity of the calculation, you can assess by estimating what you get at order epsilon squared. And once we actually have epsilon squared, then we'll be able to do it more rigorously. But for now, we have estimates. So this was an estimate that I had from this 2014 paper of just isolated black holes. And you see that the regime of validity of the theory is controlled by the spin of the black hole. So below this line, you're able to use perturbation theory. And above this line, you can't use perturbation theory because the calculation is not internally self-consistent. So we know when our calculation makes sense and when it doesn't. And the same thing is true in our merger calculation. So here is time in the simulation. And again, above this line, or there are three different curves here, each for the different values of spin that we put on the black hole, so three different simulations. And for each curve, above that curve, you're not allowed to use perturbation theory because the calculation is not internally self-consistent. And what you see is that for very low spins, again, you have access to a large range of this extra length scale that you want to probe. And for high spins, it's about order 1, which is what you usually expect for perturbation theory. And then after merger, all of them are around order 1. And in fact, this number that you get here is just set by the final value of the spin of the black hole that's left over. And it's about the same for the three different runs, which is why they all kind of agree. And in fact, that value that you get there is roughly the same as this value that you get here, which was computed in totally different ways using different code, different methods. So I think this we understand where our theory makes sense. Okay, so the most important question for LIGO people to ask is, how can you actually measure this in the phase of the gravitational waves that you observe? So right now, we don't have the predictions of the gravitational waves. That's what we're working on. But we can predict it from things that we can extract from the order epsilon to the 1 calculation. So you can kind of do a quasi-post-Newtonian-ish calculation, just energy balance, to ask how much is it going to change the gravitational wave phase. So you can read this later if you really care, or read our paper. But the punchline is that you can get an estimate for how much deviation in phase there will be when you change the theory with respect to general relativity. So if you take a GR waveform and you pick some time to match the phases and match the frequencies, then relative to the GR waveform, there's a phase difference as you go away from that matching time. So if your phase sensitivity of your detector is, say, I don't know, a radian or something like that, whatever your phase sensitivity is, if you don't see any phase difference in your whole observation over the whole in-spiral merger ring down outside of the phase margins of your detector sensitivity, then you know that whatever this small parameter is was small enough that it made this phase difference smaller than your phase sensitivity. So you can make this more quantitative and say, what kind of bound can you place on this new this new length scale L from observations like GW 150914, except if they had these different values of spin on them. So if the spins had been consistent with spins of 30% maximum, then you would have been able to bound this new length scale at the level of 10 kilometers-ish, tens of kilometers. And this is to be compared with what you get from solar system observations that can also bound this number. But the numbers that you get from the solar system are about 7 orders of magnitude worse than what you get from gravitational waves. This is why we need to go to the strong field regime. Okay. So there's a lot of stuff left to do in the future. As I said, Masha is hard at work on order epsilon squared. After these things are actually stably running, then of course the goal is to run a lot of simulations and actually get waveforms all over parameter space. Once you have waveforms all over parameter space, then you can build what's called a surrogate model. So you can use that to do Markov chain Monte Carlo with the gravitational wave data that's already in hand and actually constrain this new length scale of the theory. Constrain the theory. So we need to understand whether or not the waveform models that we would get out of this theory would have degeneracies with general relativity, which would make it more difficult to constrain. Eventually, in the distant future, we'll be able to do some Bayesian model selection, saying between general relativity and this other theory, what are the odds ratios for these two different theories? So is it 100-to-1 GR to this other theory? And then, all of this stuff that I described was for Chern-Simons, but the technology is not specific to this theory. It's true for any theory that has a continuous limit to general relativity. So at that point, it's just replacing the right-hand sides in all of our simulations and turning the crank and just running more simulations for more theories. Then you can start to do the types of things that I talked about at the beginning of the talk and try to build some theory-agnostic parameterizations. You'll see what kinds of phenomenology is possible in different theories, and you'll know what kinds of parameterizations you need to encapsulate all of those. So what I want you to remember about this, the specific work that we've done is that we have the first binary black hole merger simulations in dynamical Chern-Simons, and in fact in any theory except for Brans-Dicke. The in-spiral has qualitative agreement with work that we've had in the past. The merger, we have new phenomenology which we could never have predicted from just analytical calculations. We've been able to estimate what kinds of bounds LIGO would be able to place on the theory, and these estimates will become actual bounds in the future. For better bounds, you want signals with a higher signal-to-noise ratio, longer waveforms, which means lower mass signals at fixed SNR, and if the spins are higher, then we can, of course, bound this thing better. So, work is in progress, and if you want all the gory details, look at this paper. So, the really big picture, not just this work, is that general relativity must be incomplete. I hope that you know in your heart of hearts that, it's a good description, but it's just an effective field theory. We want to understand it better. You can do that either by trying to probe the theory itself, just learn more about general relativity and where there's interesting phenomenology. But we should also take the observational standpoint and say, LIGO gives us access to the strong fields, and we need to be able to do tests there. Right now there are tests, but we don't really understand how to interpret them at the level of the theory, so we need better tests. So the challenge to us is to find space-time solutions in theories beyond general relativity. Our contribution was the first black hole mergers in dynamical Chern-Simons. But as I said, these methods are valid for all sorts of different theories. So there's obviously still a lot of work to do, so stay tuned, or you can help us out if you want. So that's all I had to say, and I'll be happy to answer any questions. Anybody? Yes?
So what's the significance for your constraint on the length scale besides it's better than the other?
What's the significance?
Yeah.
What
does that mean?
What does it mean? Okay. Well, remember this. Okay, so first of all, it's just an estimate of the constraint. I'm trying to be conservative here. It's not actually a constraint. It's an estimate of the constraint. But if LIGO does not see anything different from GR, then you'll be able to say that this particular higher order term in the action has to be down by at whatever level. This epsilon is smaller than, maybe in the future we'll be able to put it down to the 10 to the minus 3 level or something. It's telling us what the action for gravity is allowed to be. There are, in principle, an infinite number of terms that we could add here, and this is one that we can squish down a little farther. Yes?
This may be totally silly, but if you can experimentalist, I noticed there's an axiom signal that you also predict is produced directly.
Yes. Yeah.
Right.
Right. So I called this the axion. It's very much like an axion. Then there's the question of whether or not what people are looking for in direct axion detection, like shining light through a wall kind of experiments, is the same axion. So, if you ask the string theory people across the street, then they'll say, oh, there are lots of axions. There are 80 different types of axions that you get in string theory or whatever. So I don't know whether or not this axion is the same, has to be the same or different from the axion that's coupled to, the electromagnetic FF tilde. So if it's the same one, then in principle, as it comes by your electromagnetic field, it converts some of your photons into other photons. I don't know. But yeah, this is, you're right, this is a truly radiative axion field that just propagates through the universe. I haven't really looked at the shining light through walls experiments to understand whether or not this would, whether or not this is a detectable signal or not. I don't know. Yeah.
So we know of theories that recover the art in a very non-linear way. For example, massive gravity, without a spring mechanism. Do you think there is any hope that you can adapt the formalism to cover something like that?
Yeah. I hope that something like DRGT or Hassan-Rosen can be simulated on the computer in the future. I know that it has some issues below the decoupling limit in terms of, if you want to set the decoupling, or if you want to set the lambdas that you get in that theory to be appropriate for screening on cosmological lengths. I know that you have issues there. And I'm not sure if those are cured by nonlinearities. So, if the